Welcome to the chemical engineering training video. Today, you will be the chemical engineer and let's design a Haber process plant. First, we need a tank. Well, technically a reactor. It should be cheap, chemical resistant and structurally strong. Let's consider some materials for the reactor. Ceramic is cheap, has high heat tolerance, but is brittle, so this isn't a good choice. Platinum is both inert and strong, but it's too expensive, so it's not a good choice either. How about steel? It's cheap, easily available, has high tensile strength and is inert to hydrogen and nitrogen. So we shall get a steel tank for our reactor. The next question chemical engineer asks is, how can we maximize the production? In the Haber process, 3 hydrogen molecules combine with 1 nitrogen molecule to produce 2 ammonia molecules. This reaction is exothermic. According to the Le-Chatelier's principle, the system will adjust itself to counteract the effect of applied changes. As Haber process is exothermic, we treat heat as the byproduct of the reaction. So to maximize the production of ammonia, we would want to use low temperature as it shifts the equilibrium forward. And we want to use high pressure as well, as there are less molecules on the right hand side. Typically, the process condition is set at 400 to 500 degrees C, which is sufficiently low to maintain a high rate of reaction. The pressure is 15 to 25 megapascal. That is the weight of 500 adult elephants acting on a 1 meter square board. If pressure and temperature overshoots the limit, the plant might explode. So, we need a monitoring system to look after the pressure, temperature, and flow rates. A typical system might look very complex, but safety measures such as emergency shutdown and alarms are often included. Great! You now know how to design and control a basic ammonia plant. Job done! But as a chemical engineer, we ask, can we further maximize the production? In chemistry, we learned that catalyst is any substance that increases the rate of reaction without undergoing permanent chemical change. So let's consider using catalyst to improve the reactor's performance. Iron is the catalyst for Haber process. The powdered form is used as it gives large surface area for catalytic reaction and increases the production rate. In real life, hydrogen and nitrogen gas are passed continuously through a series of beds filled with iron powder to increase yield and production. However, catalysts can come in many other forms. It can be solid, liquid or gas. They can have funky shapes as such, and chemical engineers play a huge role in designing them. It's complex, but it's exciting. So up to now, we have learned material selection, control engineering and product optimization. Next, we will consider product extraction, one of the most energy-intensive phases in a plant. At the outlet of the reactor, there are still some nitrogen, hydrogen and ammonia produced. The question is, how do we get just ammonia? There are many ways to separate mixture. For liquid mixture, you can use fractional distillation that separates components of different boiling points. You can use a solvent to dissolve specific components and extract them. For solid liquid mixture, you can use filter to remove large and suspended particles, or simply just let the solid settles down, a process called sedimentation. For gaseous mixture, we can use membrane separation, solvent extraction or condensation. In fact, condensation is used in Haber process. We use cooling water to reduce temperature and liquefy ammonia gas, which is then collected. The residual hydrogen and nitrogen gas will then be recycled to maximize the use of raw materials. We have come quite far and we are almost done. Now we will proceed to the last and perhaps the most important stage of design, which is the waste management. As a responsible engineer, we do not just dump the waste into river and atmosphere, as we need to comply with environmental regulations. Wastewater treatment and air scrubbing systems are often installed to prevent emission of toxic substances. For our ammonia plant, we will install a scrubbing system to remove harmful waste products. Phew, that's intensive! But you have just learned the 5 key stages in plant design, which are material selection, control engineering, production optimization, product extraction, and waste management. And congratulations, you have just designed an ammonia plant on your own. Hope you enjoyed the video and thanks for watching.